All right, so this is the final video for chapter 9. We're going to do some examples of using logistic regression. So again, red's going to be when I switch over to R, but otherwise, please pause, copy this down, and then press play. Okay, so we're looking through example 9.12, and this is the scenario where X is going to be the age of a driver involved in an auto accident, and Y is going to either be 0 if alcohol was not involved for the driver, or 1 if alcohol was involved in the driver. Okay. All right. Well, since Y is Bernoulli, it seems likely that a logistic regression model might work. So P sub I is going to be the probability that driver X sub I had alcohol involved in their accident. And I'm going to flip over to R, and we're going to figure out how we get the slope and intercept coefficients for our logistic regression model. Okay. Okay, so I'm up here in our notebook on line 145. I've got the resample package clicked. And if I look to see the fatalities data, if you look at it, we've got age in the rightmost column, and we've got alcohol either being 0 or 1, involved or not involved. So that's the data that R is crunching away at. And this line 146, it's going to fit a GLM for alcohol as a function of age. Data is that fatalities notebook. And the family we're using for this generalized linear model is binomial because the Y's are Bernoulli distributed. All right. So I'm going to run that fit command. And the data class for fit and the help GLM will, just as you see, give you some information about GLMs. All right, so I'm going to run line 150, and that's going to give me the coefficients and some other basic information for this generalized linear model. So the coefficient, the intercept is minus 0.123 if I round, and the slope next to the age is minus 0.029 if I round. Also gives us some other information. Or I could have just asked for the coefficients that fit, and it gives me the coefficients in a different format. Or I could ask for a summary of fit, and we get the intercepts, the slope, and some additional information. The rest of this code, I think we're going to go through in class because it's a bit more complex. It might be easier in person after we've messed around a little bit. All right, so please note, the intercept was minus 0.123, and the slope was minus 0.029. So intercept minus 0.123, slope minus 0.029. Okay, so let's ask a question. What is the probability that alcohol is involved if the driver in the accident was 20 years old? Okay, so I can take my logistic regression model, pop both sides up as a power of E, and plug in X to be 20. And this exponential value cranks out to be 0.495. I can multiply my 1 minus P over to the right, run the 0.495 over through the parentheses, and add 0.495 P hat back over to the left to get 1.495 P hat equals 0.495. Divide by the 1.495, and I get 0.33. So there's a 33% chance that alcohol was involved if the driver in the accident was a 20-year-old. Okay, that's high, right? Well, here's the actual question. Let's compute the odds ratio of a 25-year-old versus a 35-year-old driver involved in an accident having alcohol involved. Okay, so I'm looking for an odds ratio. So there's my 35-year-old driver, P2 over 1 minus P2. There's that person's odds. P1 over 1 minus P1 is the odds for the 25-year-old driver. And from our previous video, we know that this odds ratio is equal to E to the beta times delta X. Now, our X1 is 25, our X1 plus delta X is our 35-year-old, so our delta X is 10, okay? So there's my beta, minus 0.029, there's my delta X, and I get 0.748. So the odds ratio is 0.748. That means the odds of alcohol being involved drops by 25.2% per 10 years, okay? So let's think about that. That odds ratio, it's 0.748 over 1. That denominator was the odds of the 25-year-old having alcohol involved in comparison with the odds of a 35-year-old having alcohol involved. And so the numerator is 0.748 the size of the denominator. So it's 25.2% smaller. So the odds have dropped by 25.2%. And if you notice in this calculation, the value of X didn't matter. It was just the value of delta X that mattered. So this 25.2% drop in odds occurs at every 10-year increase from a 25 to a 35-year-old or from a 23-year-old to a 33-year-old. Okay, it's just about the delta X. All right, let's look at another example. We won't use R for this. So you could pause, copy it out, and press play. All right, so one thing, hospitals, like in the last 20 years, hospital stays have decreased dramatically. Like people aren't staying in the hospital as long as they used to, and it's for two reasons. One, health insurance doesn't want to pay for hospital stays. They're expensive. And two, hospitals have realized the longer a patient stays in the hospital, the more likely they are to develop a hospital-based infection that could be really tough to kick. All right, you've heard of super viruses or things that most of our antibacterial medications can't kill. Oftentimes they're found in hospitals. All right, so a hospital did a study. They're going to let X sub I be the number of days that a patient is hospitalized. Now, Y sub I is going to be 0 if they leave the hospital not having had an infection, or 1 if they leave the hospital having had an infection, or I guess maybe they don't leave the hospital if they die, but they had an infection. Right? And so that's Bernoulli. So it makes sense to try a logistic regression model on this thing to figure out the probability of getting an infection based on the number of days you've been hospitalized. And the question is, how do the odds of getting an infection change for someone who stays an additional week in the hospital? All right, so let's say we had a data set, we throw it at R using the commands we just showed in example 9.12, and we get a logistic regression model. Now remember, I'm putting a hat on the P because this is R's approximation of the probability. It's not the truth, it's the model of the probability. So there's a logistic regression model, and we're looking for the odds of getting infection changing for someone who stays an additional week. So our delta X is an additional 7 days. So we're going to do the odds ratio, P2 over 1 minus P2, P1 over 1 minus P1, P2 being however long the first person stayed plus 7 days plus the delta X. So I get my e to the beta times delta X. My beta is positive 0.023. My delta X is 7, and I get 1.175. So the odds have increased by 17.5% for each additional week I stay. Right? Okay, so logistic regression model. It's a linear model. Sometimes we have to futz around, as in the last example, to actually drag out the actual probabilities. But if it's a ratio of odds that we're looking for, that's relatively simple. All right. One more panel. Okay, so just a little bit about sort of the what's happening in the background here, or how are we going to do some things that we'll work on in class together. If we want to do some inference in this with a logistic regression model like confidence intervals or something like that, we're going to have to use R to find some standard errors. And if you recall from our work earlier in this chapter, standard errors are sort of necessary to figure out a lot of things. So we're going to use R to find the standard errors, and then we can then use those standard errors to determine things like confidence intervals, t-stats, hypothesis tests. Okay. And unfortunately, it is the case that for logistic regression and generalized linear models in general, we oftentimes need a large n value. So that function, that natural log of the odds, that sort of is hiding the variable y sub I. It's transforming the data and sort of flattening it a little bit. And so because of that, we oftentimes need a lot of data to really get a good fit for this flattened data, right? Or if we don't want to use standard errors, we could just use bootstrapping and or permutation techniques to get confidence intervals, p-values, et cetera, as we saw in an earlier video in chapter 9 as well, okay? All right, well, if I'm going to use R to find some standard errors, we better make sure we've got some assumptions met. So what are the assumptions for finding standard errors? Well, we better have actual data. So our X values better be fixed and not just randomly generated and assigned to Y values. The X values better have a linear relationship to the natural log of the odds. That's the heart of the linear regression model. This natural log of odds is equal to an alpha plus beta xi. If that relationship isn't actually there, if there isn't such a linear relationship, our model's crap anyway, okay? The y values better be either 0 or 1, or else we probably shouldn't be using the linear regression model. Sorry, the logistic regression model. And the y values better be independent of each other, all right? So that's sort of happening in the background. All right, so we're going to do some more work on like confidence intervals and whatnot for logistic regression in class.